Okay, so today's topic is about sampling. Um, I made a couple of last-minute modifications to the exercise, but anyways, the so sampling it is anyways. So I will probably start by reviewing the what is required in order to get a good sampling of a signal. This is actually partly covered, at least partly covered on digital signal processing course, also on the measurement systems fundamentals course. Those topics are covered. I have my own set of slides explaining what it is all about, the signal conditioning. So let's take a quick look if I can go through these slides. Oh yeah, so that's actually a part of some other course in Finland I'm giving called Sensors and Interfaces. Okay, what sampling actually means, or what what is required in order to get a sample into computer? Okay, simply we need some hardware. Okay, we need a signal conditioning, which is the first part there, the gain low pass filter, which is analog low pass filter. You always need some sort of analog low pass filtering on before the A to D conversion. Some of the A to D converters are less the sensitive for the on that off the band noise, but at some point you need that the low pass filtering done. Then the sampling process. I have this S/H, which is sample and hold circuit. With some A to D converters, like successive approximation A to D converter, you need a separate sample to hold circuit to keep the value of the signal during the conversion. And then, of course, there's the A to D converter after that. And if you are taking a look at the signals, what they look like on each of these steps. So first of all, we start with the analog signal. And if we had a oscilloscope, you usually see a lot of noise on the signal. And the reason why we have the gain and there should be also biasing is to actually match the signal range as well as possible to the A to D conversion range. Okay, then next step that after the low pass filtering, there shouldn't be any more these quickly changing signals. So fundamentally, we have to remove all the frequency components which are higher than the Nyquist frequency. So if there are higher frequencies than the sampling rate divided by 2, you have to reduce those ones. So that's the anti-aliasing filter, low pass filter before sampling. Okay, on that step we have a sampled analog signal. So basically now we have discrete time, but we still have continuous values. The value can be anything, it's an analog. And just after the A to D converter, you actually have these levels, the binary levels there, which actually then gives you the final digitized signal. So basically, it could be, for example, something like that. So those purple lines here represent yes. G is gain, amplification. Okay. So after that, you have a digital signal or digitized signal. So that's the same thing in that kind of blocks. And uh, the final signal is digital signal which is discrete in time and quantized value. And that actually also brings us a new noise called quantization noise. Okay, good, and that's a cat. So amplification and bias, I'll just go through this quick sampled signals. This is fundamental, this is the same as previous. You have already probably familiar with this discrete time and continuous value kind of sampled signals. That's the same as digital signal processing. The Manfred Junke's course mostly covers the mathematics or the tools for handling discrete time but continuous value signals. Okay. Aliasing. Okay, you understand the aliasing, right? So we have the real analog signal, and if you have a sampling rate is too slow, you get that red kind of slowly varying signal there. So basically, to prevent the aliasing, you need to remove the or reduce enough of those high frequency components so you can actually sample the signal as it is, or go into higher sampling rate. But usually you cannot. All right. And the anti-aliasing filter is simply a low-pass filter to reduce those unwanted frequencies. Usually, the stop band actually starts on Nyquist frequency. That's a usual way of designing a anti-aliasing filter. Today we are not designing filters. If you are interested about the filter design or digital filter design, then next fall, Sakari Lukkarinen will come here. He has the DSP problem solving with MATLAB course. Have you already been there? Some way actually attended that one. Yeah. So there's a FIR and yes, Sakari. Yes. So there are actually the FIR and IIR filter design there. So to make a better filter. Today we are just averaging. Okay. Yeah. So we have a quantization noise, and signal to quantization noise ratio has a definition. Who cares? Right. So let's see, what else do I have here? That's all, maybe. Yep. So that's just a short review of the of signal conditioning, what is this all about. Okay, let's take a quick look at today's exercise to see what kind of things we need. So, that's what we need to do on today's exercise. And all of this inside of one single piece of circuit. So I will show you how to design a low-pass filter. Since we also have these analog blocks, there are two types of analog blocks. One is the continuous time analog block, but there's also the switch capacitor type of analog block. Switch capacitors can be used to make filters, analog filters. So fundamentally, a switch capacitor is actually same as variable resistor. Okay. Have you got the switch capacitor technology on on the electronics. Well, just take my word. Well, uh, maybe I can actually elaborate a little bit. So if we have a, let's see, switch here, another switch here, and then we have a capacitor here. Basically, if you switch this one down, you can uh, uh, send a charge delta Q here, and when you open it and switch this one, you can actually move that charge here. So basically, the amount of charge transferred here depends on the voltage difference, right? U1, UC, U2. Okay, so that one depends basically on which voltage was here. And if it was switched like that before, it was U2. So basically we get a charge, here's delta U over C, right? Okay, so basically we start switching these like, you know, on, off, on 90-degree phase. We get a control of how fast the charge goes from one end to another one, which fundamentally at high frequencies, this starts to look like a resistor. And this switching frequency is actually controlling the how much current you get through. So the resistance or conductance. Okay, so that's simplified explanation what the switch capacitor technology is. So now if we have a switch capacitor, capacitors inside of a circuit, integrated circuit, and then we of course have these constant capacitors. We can easily do there the second, or for example, second order filters, like the let's see, voltage controlled voltage oscillator, VCVS, SVCVO, the type of filters. Okay, good. So we have the analog low pass filter. After that, we have A to D converter, which was yesterday's topic. All right, then on software, a little bit more of software. How to handle a stream of data. Basically, this is a common way of doing measurements in small computers, like, well, anything. So the end result is downsampled from the original one. So we have a much higher sampling rate for the original signal than for the result. For example, if you are making a measurements of AC power, you are measuring this voltage and current at higher rate to calculate what was the power on the measured power, and the power actually doesn't it has meaning only, say, within 1 second time frame. Here we have a little bit different situation. We are just using higher sampling rate, so oversampling, and then we need to downsample to get, you know, a nice constant stream of data. Okay, good. So, yeah, and after the downsampling, that is LCD, of course, show the result as a string to LCD, and also send the result as a string to serial port. Okay, so basically this takes a little bit, say the analog low pass filter takes a little bit more time to do on the hardware, but the rest of those you have already done. So today's exercise is more about the software. Some tricks for that one. Let's see if I can move this one without. Okay, now froze again. There, now it works. Okay, so what I'm talking about here is just a moment, I'll check that. Yeah, just more or less shows up on the stream. So, let's see. So the analog signal basically, although today it comes only from that variable resistor again, just for fun. Tomorrow we have some real sensors, I think. Yeah, we have some real sensors tomorrow. So that sensor, then maybe an amplifier. Well, I will just mark it as A. You probably need an amplifier with amplification of 1 because of the routing. We don't know that yet, but that's my guess. Then we have the low pass filter. So basically I want to get rid of some of the noise already on this path. And then A to D converter. Okay, and then it goes to digital. So that's done on hardware. Then on the software side, you take this stream of data and put that through a low pass filter in digital domain. Okay, and then downsampling. Let's see. I think the ratio was 1 to 50 downsampling or something like that. I don't remember it exactly. It's actually on the exercise. So that's downsampling. So this low pass filter is needed to avoid the any the aliasing effect on digital sampling. Okay, but we will do a shortcut since that otherwise it might take a little bit too long. But if you have already knowledge how to do a low pass filters on small embedded systems, be my guest. Go ahead, do it. It is doable actually with the PSOC 1. You can do up to fourth order on that sampling rate what we have there. It has been done. All right, and then just display. Yes, downsampling. Let's see. So that goes to LCD, and then we have the display. Not, but it's not display. The COM port. Okay. I need to still, I probably have to define the speed for the comport. See, do I have the speed? Yeah. So 38,200 bits per second. Was it 38,400? Whatever. A constant rate. A constant rate. Yeah. All right. So actually, shortcut on this part. Let's not make it too hard. We use a running average filter here. So we calculate the average of ADC, the results basically during that was half second. So the final sampling rate is 2 samples per second. Okay. So fundamentally, here you have the sampling rate something about 100 samples per second. It doesn't need to be exactly actually on this exercise. It's nice if you get it exact. You can try to do it. If you cannot, then you just get the values as fast as you can. Okay, so that's 100 seconds, and that's 0.5 seconds. That's 100 samples per second. So on half second, you get how many samples? Original samples. This is a trick question. You get either 49, 50, or 51. Why? I'm quite sure that on some case the timing varies because of you are doing something else on your main loop when the interrupt comes. So you do not necessarily get exactly 50 samples for this half second time frame. So anything between 49 to 51 samples here, which means that on your software you need to have the a sample count value that you will increment, and then you would have the ADC sum that you will increment by the step of the ADC value. Okay, and that is done. This part can be done. This is quite fast since the incremental of a value will take, something like few microseconds. I think, yeah, 24 megahertz. So it's about roughly few MIPS computer what we have here. So I would say this takes few microseconds to calculate. This the addition is usually takes more than that, especially since we do not have any more the native word length here. So We have 8-bit processor. Okay. And this one requires at least 16 bits. You need to do the calculation how long variable you actually need to avoid the overflow. You can easily get overflow on this kind of when you start adding 50 values. Let's see, how many bits is 64? 64? Yeah. How many bits? 6. 6 bits. Right. 64 is 6 bits. So you need at least 6 bits extra compared to that A to D conversion value to avoid the overflow. So basically 16 bits in this case, and if you use 2-byte integer, you can have 10 bits for the A to D conversion. Not more than 10 bits. Okay, but anyways, so basically this you should do for every single A to D conversion result. You add sample count and then sum. Then every half second, you then take these two new variables, okay, just make copy of those, okay, then initialize those again, so you have to put those to 0 again, so that when the next interrupt comes, you can start counting from the scratch again. And then use the copies to do the division. Division takes at least 200 instruction cycles on this 8-bit processor. Division is slow process. Multiplication is a little bit faster, but division is generally the slowest instruction on a processor which does not have any mathematical unit. Like, most modern processors do have the mathematics unit, but this does not, this 8-bit processor. The only speeding up component there is actually it has a MAC, multiply accumulate unit, which probably helps already here without you knowing it. Okay. So that happens on 100 times per second, and this happens on 2 times of second. Alrighty, so that's today's exercise. Oops. Video. Any questions? All right. If not, I will show you how to initialize the low-pass filter. All right, so we're talking about this. Oh, no, but nobody told anything. It's not there yet. Okay, there we go. So, the analog low-pass filter. How to actually put that one there. All right, I'll just close that. Start from scratch again. Just a moment. That's 400, right? Okay, let's start it from scratch again. New project and name MTKP exercise 4. Okay, so let's start by adding a analog low pass filter, and we will be using that LPF2. Okay, and there are different kind of topologies you can use, actually 4 different topologies. Basically the difference is how the digital blocks are used. This one is as good as any. It's a vertical uh, the filter topology, and there just click OK, and this takes 2 blocks on the 2 analog blocks, no digital blocks. Okay, and you need to reroute the signal for this one. You know it from the yesterday. For example, I'm not showing it to you. You know how to do the rerouting of the signal. Okay. You can, if you wish, change these values by hand. However, I would strongly recommend you to use the wizard. Otherwise, there's absolutely no guarantee you get the parameters correct. There. Doesn't it look much better? And we basically are shooting for a corner frequency of about 10 hertz. How to do it? Basically, you go and start reducing these. Let's see. Does it go to that one? Yeah, it actually does. That's nice. So now I got 14 hertz as the corner frequency. Why am I using that much of the low pass filtering? Well, remember that basically our final the sampling rate will be 2 times a second, which means that the whole range for the final result is the sampling rate was 2 hertz. Everything is actually less than 1 hertz. Okay, and so that's where the information band is actually. I'm not doing the design for lower than 10 hertz because then this system doesn't anymore work well. That picture what we have here this is not the full picture. Basically, that orange line starts rising again. So this is not good for very high frequency noise, but it's good for, well, we have the signal coming from this turning wheel or whatever that, yeah, the variable resistor. So that's good enough for that one. Okay, so 10 hertz. All right. And this one now shows that the sample rate for this meaning the switching rate is 120. Okay, and make a note of two numbers here. The column clock should go at 480 hertz. So that's what you need to generate somehow. You cannot generate it using this, sorry, using this VC1 to VC3 anymore, since this is only 400 hertz, and you need a divider of 50,000 from the system clock. Okay, so the divider is 50,000, and column clock is column clock 480. Since this is one of the parameters we need. Okay, that's fine. Otherwise, it looks good. Well, decent at least. Yeah. Gain 0 dB decibels. So it's 1. Yeah. Gain 0.0 decibels. Gain of 1. Right. It's unity gain. There. Ha. So how did you guess that C1 is 10, C2 is 10, C3 is 20, and so on? Okay. This module, I would say that it's almost impossible to be used without that wizard. You can try and fail. All right. Okay, and then we need the signal input. I'll just take it. Well, just for fun, I'll just take it from there and, add the amplifier later. This is your part of design. Get a routing of the signal done correctly, so that on exercise I'm asking this input signal to come in from where? Okay, use port 0.2. Yep, for analog signal. Okay. You can actually, and sometimes it might be even a good idea, to run the signal to analog bus from this block. So basically, then you can take it out from the pin 0.3 in this case. In case you want to check if, let's see, since this one has only calculated value, so it's just a nominal is a blue one, then this that expected the orange one. Okay, you can actually test it yourself, how it functions, by taking the signal out. All right. Comparator put was also disabled. Polarity. All right. So basically, this is using Salenki kind of design, either inverting or non-inverting out polarity. So to get positive output from positive signals, you check the non-inverting. What else? Modulator clock. All right. That's something that we need, that 480 hertz signal. Then, of course, we also have the COM port. Compot had, in most of the design, I think this was 8, was it? 8, maybe? And that one was something else. Okay. So basically we can start maybe by using a couple of these VC voltage divider clocks, or are we in luck? And let's see. We have that. Oops. We have bitrate clock, baud clock for our the compot. Maybe we can use that one. Since it's already down down samples from the original, and that might actually be might be close enough for this one. I would guess so, since they are 38,400. Well, maybe. Well, I'll do it in any case at some other way. So this is one way. We already had VC1. Okay, that's 3 megahertz signal divided by 430. That's about 7,000. That's awkward number. How about 15 times 8? 120. Yeah, that's closer. Okay. VC2 would have now divided 120. And we still need to divide that by, the divider should be in total 50K, that's divided by 120. 416 or 470 division more. Good morning. 5 minutes or 10 minutes. 12. Make it 15. All right. No? Yeah, I will give you a call. Yes. All right. So, in principle, I don't care how you get that 480 as it is close enough. And the question is how close it has to be. Take a look at that one. What happens if you have, say, 600 hertz? Well, if it's 600 hertz, it would be the column clock for 80 hertz, see, 480. 600 divided by 480 times 120. Okay, what would happen is something like this. Not much. So you don't need to nail this frequency exactly, since it's still it doesn't affect much of anything. It just shifts the corner frequency accordingly. So at least as long as you get it on this range, it's good enough. But anyways, I had some trouble here. Let's see. So 400 and something. So 400 and something would be 16-bit timer. Anyhow, if you had already that clock, yeah, let's see how much it was. 38, 24, divided by 4 equals 62 times 8, 500. Oh. 78. Oh, well, that actually gives better. Well, we have digital blocks, so we can actually run a 16-bit timer here. 16-bit timer. Whoops, why I clicked it like that. 16-bit timer. Clock, for example, VC2. Capture was probably low. Terminal count out now. Oh, actually, yes. Yes, none. Compare out. We are not getting this signal outside of the circuit. But period, I have to click here. It's the 417. Compare value does not matter. Compare type, you just check something. Well, interrupt type, this will not interrupt. It's just, I've just put the interrupt to something there. Sync the sys clock, full clock. That one, and that's basically all we need to do on the design. Take a closer look on the timer, the datasheet, basically, because I'm always a little bit unsure about the capture. Okay, the software capture mechanism will not operate correctly if this parameter is set to value of 1 or held high internally. That's why actually I held it low. And then how to take this signal down here. So that's basically the column clock we need to check. And that column clock comes from this multiplexer. Maybe I should actually show it better. So it's this multiplexer actually which is used for that 480 hertz signal, and basically we can go VC1, VC2, or either of the multiplexers. Now it's actually on this multiplexer, which is then I can connect this one to DBB01. Yes. Okay. Now we have a connection from this timer down to the this column clock select, and down to this as the low pass filter sampling clock. Okay, so fundamentally that's all you need to do to make the low pass filter running. Plus, on the software, in order that module to run, you must start it. But not only this module, you also need to start the timer module that gives the clock signal for that one. And not only those, but you need a programmable gain amplifier there. And yes, you have a question. So the 16-bit timer output is on this DBB01 block. Okay. And that's, you can connect that one clicking this multiplexer. It's the second DBB01. It relates to that one. And then this one here, analog column clock. This doesn't have any other outputs. No other outputs. Yep. Any questions? Timer setting? Well, it doesn't matter what kind of interrupt you use there, since we are not using the interrupts. But you just select something that you don't get the warning. Um, got it? Good. Okay. And Sven, uh, hopefully you can. Yeah, you may need to move those so you get the signal to A to D converter. Of course, let's see if we put the A to D incremental. Yeah, let's see if we put that one there. ADC Inc. Can we take the positive input from ASD to? No, it doesn't. It doesn't allow me to take the AD value from that one. Okay, there are several ways you can trick trick this. Yeah, yeah, yes. Out bus to pin and then pin to the A to D converter. That'll work. Or let's see if it's possible to actually let's move some of those. Does it help if we move that one here? Wait a minute. Does it help at all? You can move around and see where you can actually start. ACB03 would be okay. Doesn't work that way. Okay. No luck. So I think the correct way would be to move it to analog bus port 03 if it's not used otherwise. Then you can take the port 03 signal, for example, oops, not that way. We'll put a gain of 1. You can connect the let's see, amplifiers, BGA. BGA1 can have input from the multiplexer, which goes to 03, and then that signal can be selected, probably positive input ACB00, yes. Oh, okay. And this is something we did already yesterday. The signal of this one, the input of the low pass filter would be from ACB01. So it kind of goes. There are so many ways you can route the signal. On analog part, you need to really just try it out and see how you can do it. If nothing helps, then you can always try to do a different topology of the filter, since that basically means where that block is located and how it can be connected to the other blocks. This vertical topologies are actually such that you have to take use of the signal from the next column, but the horizontal you can take it some other ways. So that will probably work. Okay, any other questions? If not, thank you for listening. I've stopped the streaming.